Okay, calculus, we're looking at the final part of this whole related rates. We're going to be starting with example 9 from the AB manual workbook. Remember, so far we've talked about what a rate is, how to notate it, taking the derivative with respect to time, etc. So let's jump into this one and see what we're looking at here. Okay, so the first thing it says is sand is being poured on a beach. Now I know this is not the same cone that you guys have. You guys actually have a cone that looks like this. But that's not really an accurate cone. It's more like the shape that I drew here, and we're going to go over why here in a second. It says its radius is always equal to twice its height. So that means the radius is going to be double whatever the height is. So if this was like 1, then the radius here would be 2, and the whole diameter would be 4. So that's a more accurate picture there. But I want to stop right there too. That says radius is equal to twice its height. If I were to notate that kind of as a math equation, I would write r for radius equals twice the height, so that's going to be 2 times, we'll say h for height. Okay, so that's some information there. We're going to be doing more as well, but let's look at what we got next. Okay, so then they say if the sand is poured at the rate of 20 inches cubed per second. So this cubed is kind of a clue here too, because we know this is a rate. It's going to be d something dt. So d, and then we know there's going to be a letter here, d dt, and it's going to be equal to 20. And the fact that it's inches cubed, that's very specific. That means that if it, remember, if it was squared, that would be area, and if it was just one dimension like length or width or radius or height, that'd be first power. But this is triple dimension, cubed. That means this is volume. dV dt is what we're going to write in there. Okay, so dV dt equals 20 inches cubed per second. Rate equals 2h. And now this dV dt is also my other big clue. It says how fast is the height changing? So we want to know dH dt, that's our question. It equals what? And we're going to be checking it when h equals 2 and when h equals 6. All right, so let's find an equation that we can use. A pretty common one here, this whole conical shape, is just doing volume or surface area of a cone. So, well, volume of a cone, let's start with that. Volume equals, and of a cone, it's like a cylinder but pointy, so we're going to have the pi r squared h, but because it's pointy, we have to multiply that by a third, or divide by 3, however you want to say it. So we'll start with this. And we're actually going to run into a problem here. We got these dVdt's, dHdt's. We don't know much about the r. And this r equals 2h is going to kind of save us in the end, but we're going to see something interesting happen. So let's take the derivative. Let's do ddt of everything. ddt of this and ddt of this. Well, that means on the left side we're going to have dv dt. Hey, we can plug that in. That's going to be helpful there in a minute. And on the right side here we're going to have 1/3 pi. That's a constant, so that just stays. Now we have a product rule, r squared and h. Okay, so r squared times the derivative, so a times the derivative of b, so the first one times the derivative of the second is going to be r squared times the derivative of h is going to be dh dt, plus, now we're doing the other way around, h times the derivative of the r squared, which would be 2r, and then dr dt. So here's where we hit a snag, you could say. I look at this first term, dv dt, and that's cool. I know dv dt, I can plug that in. I look at r squared here. Well, I don't know what r is, but I know that h is 2 for my first one, and if I plug that into here, I could find r, so I could take care of r as well. I know that I'm going to be looking for dH dt, so that one, we'll be finding dH dt. That's going to be our key right here. But the big kind of wonder, like how do I deal with this, I can plug in h, I can plug in r, I can plug in dv dt, but this one right here, this dr dt, what do I do with that? Well, I got some options. I pretty much just need to do a substitution somewhere to get rid of the r's or dr dt's, or both. In this case, since I've already done the derivative, I'm going to just try and find dr dt and make a substitution. Well, here's where this equation is going to come into play. If I were to take the derivative of both sides, I would know that dr dt is going to be equal to 2 dh dt. Okay, now considering that, I can take this dr dt out and replace it with 2 dh dt. So I'm making a substitution there. Now let's plug some numbers in. So I'm going to plug in this dv dt equals 20. So we're going to start with that. 20 equals. And then the 1/3, that's just a constant. 1/3 pi, or pi over 3 if we can want to write it that way. Now we know that h equals 2. And if we plug that in here, that also tells us the radius is double the height, so r equals 4. So this is going to be 4 squared times dh dt plus h is 2 times 2 times r, which is really 2 times 4, times, now dr dt is being, dr dt is being replaced with 2 dh dt. We got a whole lot of stuff here. I'm going to put a square bracket around all this just so we kind of know that all those things are inside that group. Okay, so let's simplify this a little bit. We got 16 dh dt here. And for the second one, 2 times 2 times 2, which is 8 times 4. So that's going to be 32 dh dt. And I can combine those. Those are like terms. They're both just a constant, a coefficient, you could say, with dh dt. 16 plus 32 put together is 48 dh dt. Okay, so that's where we're at now. We got this pi over 3 as well. And that's all equal to 20. So if I'm simplifying even more, I can simplify the 3 and the 48. That's going to make 16 over 1. Now to simplify both sides, I need to multiply both sides by 1 over 16 pi. And I would wind up with 20 over 16 pi, which I could simplify to 5 over 4 pi, equals dh dt when h equals 2. Awesome. So the rate of change of the height is 20 divided by 16 pi when the height equals 2. A slightly different approach. So that's kind of new, actually. I barely kind of figured that out today with some students pointing it out. The way I used to do it is I would make the substitution early. So what we just did here is first we did the derivative. We did ddt first. And then second, let's see, let's take that back. Second, which is right here, we did a substitution. Alright, so I'm going to do it reverse. I'm going to do the substitution and then do the derivative. So let's substitute. We know that h, 2 times h actually equals r. We also know that the volume is 1/3 pi r squared h. So I'm going to take out this r and replace it with 2h. So we're going to have 2h quantity squared times h times pi over 3. That equals our volume. Now just simplifying a little bit more, 2 squared is going to be 4. So this becomes 4 pi over 3 times h squared, and then h to the first, that'll combine to h cubed. So now let's just take the derivative of all these. This is significantly smaller because we took out one of the variables. We simplified out the r's and replaced them with just h. So now we're taking the derivative with respect to time on both sides. On the left side we'll have dv dt. Okay, and now the derivative here, we got a constant 4 pi over 3. Then the derivative of the h cubed is going to be 3h squared times dh dt. Some algebra simplifying here. This 3 and this 3 make a 1, so those are done. And then the h, let's say that I wanted to simplify this a little bit. I can multiply both sides by 1 over h squared. And then that tells me that dh dt is equal to dv dt times 1 over h squared. Well, let's plug in our thing. So dh dt, let's just actually confirm something here. If I were to plug in h equals 2 at h equals 2, I would get the same thing. Even though this process was a little bit different order, it followed the same rules. It did everything appropriately. So let's see what would happen. dv dt is 20, and 1 over h squared is going to be 1 over 4. I'm missing a pi in here. This 4 pi. So that 4 pi is actually going to be in there as well. So let's see. How would that simplify? So I'm dividing by h squared and 4 pi on both sides. So I got the 4 pi. It's going to be in the denominator. Almost forgot that. 4 pi. H squared is going to be 2 squared. This simplified would be 20 on top. 4 times 4 is 16, so that's 16 pi. And of course we need to remember units. We're talking about the rate of change of just one dimension. So that's going to be, what are we doing, meters here? Inches. We are doing inches per second. So this is inches per second. Awesome. Okay, so we got that. Let's do the other one. dh dt when h equals 6. Well, that's going to be 20 times 1 over 4 pi times 6 squared. I guess I could simplify this 4 and this 20. That would make a 5 on top and just a pi on bottom. So we'd have 5 over 36 pi inches per second. So there's our answers. So it is a little bit faster if you substitute first, because when you substitute, what you're actually doing is you're reducing the amount of variables that we have. In this stop right here, we had too many unknowns. And we needed a secondary equation for a substitution. And that substitution allowed us to find a piece that we need. So you could substitute first, or you could do the derivative and then substitute after. But if you wait to substitute, you might wind up having some extra pieces in there. Okay, so let's do another one. It's kind of similar. It's just upside down. Oh, here we go. Before I jump into that one, I want to talk about some geometry here real quick. Let's say I have a triangle. Not like this. Let's do something different. Let's fill it with empty, and we'll just use a black line. So here's my triangle. Now if I were to do another triangle inside that triangle, kind of like that, there's something going on between these two triangles. So this one here, if it meets perfectly with it, these two are actually proportional, meaning that their dimensions are rated or related with the same ratios. So let's say this was 5 here, and the height then was 15. Well, then that means that this over here, if this was, I don't know, 3, then that means the height would have the same ratio, so it would be triple whatever that radius was, or whatever that half length was. So that would be 9. that means that the ratio between the dimensions 5 to 15 is going to be equal to the same over here, 3 to 9. They're similar shapes. And that happens whenever you have two triangles that are embedded with each other. They have a common vertex. It has to do a lot with just measures of angles, and there's a lot of proof to it. But just trust me in the sense that we got similar shapes, same proportions, constant proportions in fact. And that constant proportion is going to be how we find a secondary equation. So let's look at this one. Water is draining from a conical tank, that just means a cone-shaped tank, at the rate of 2 meters cubed. Whoa, 2 meters cubed per second. And draining, that means it's coming out. Out, 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 out. That means it's draining, it's getting smaller, it's decreasing. So it's a decrease, and that tells me that we're going to have negative 2 meters cubed per second, and that's going to be equal to then the rate of change of our volume because we're cubed. So that's dV dt. That means we're going to use volume again, volume of a cone. Hey, that sounds familiar, like we just did that. The tank is 16 meters high. Okay, so let's start with that. Here's our center point. Let's draw a pretty clean line here. The center was pretty right on there. And then we have this radius here as well that would fit into that. So this is 16 tall, and it's got a top radius of 4. Now remember that proportion thing where we have like our height equals 16 and our radius equals 4? So we have a relationship between this radius and this height, and you can almost see it just intuitively. If we look at the radius, that's going to be the height divided by 4. Or if we were to look at it from the terms of the height is equal to 4 times the radius. So this is really the same equation. One of them we'll use, one of them we'll kind of ignore, but we'll kind of see which one suits us better. So it says how fast, the question here, how fast, so in other words, what's the rate, is the water level falling? The water level is measured in the height here. This is the water level. So that's going to be our h. So the rate of the water level, or the rate of h, is going to be dh dt. That is our question mark. And where are two places of measuring? We're going to be looking at h equals 12 and h equals 2. Well, let's do it. So first, we got to start with an equation. What's our equation this time? It's the same thing as it was for the last one. That's the volume of a cone. So volume equals 1/3 pi r squared h. Now I'm going to go ahead and do that substitution. So now I'm going to do my substitution using one of these two equations here. Which one do I want? Well, I want to keep dh dt. Why do I want to keep dh dt? Because dh dt is the thing I need to solve for. So I need to keep h to wind up gaining dh dt. That means I want to get rid of, so the r is going out and the h is going in. So we want to take the r out and put the h in. So I got to take this r right here out. That means I'm going to have volume equals pi over 3, same thing as 1/3 pi, times the radius squared times h. So r is the piece that I want to take out. And I know that r is the same as h over 4. So I'm going to put that right here, h over 4. So let's do some algebra, simplifying here. Volume equals pi over 3 times h squared over 16 times h. Now if we simplify that just one more time, we're probably suited then. We got pi over 48, because 3 times 16 is 48, times h cubed. Okay, now that's not too bad of an equation. So this is going to be pretty easy. We just got a constant here, a power rule. Let's work our way through the derivative. So the derivative on the left side, if we're doing d dt of everything, d dt is going to be dv dt on the left side. On the right side, we got the constant pi over 48, so that just stays, tags along. The derivative of h cubed becomes 3h squared dh dt. So let's see what's going to simplify here. The 48 and the 3, those would simplify. 3 goes into 48 16 times. Hey, this is kind of getting familiar. dv dt is going to be equal to pi over 16 times h squared dh dt. Now at this point I can substitute if I want, or I can get this dh dt by itself and then substitute. I'm going to go ahead and do the algebra first, simplify these pieces. So that means I'm going to multiply by the reciprocal. So I'm going to multiply by 16 over pi h squared on both sides. 16 over pi h squared. So that means the pi's make a 1, the h squareds make a 1, and the 16's make a 1. All I'm left with is dh dt, the piece that I want. So dh dt on the right side. And what do we got on the left side here? We got 16 over pi times h squared times dv dt. And that equals our dh dt. So dh dt at h equals, well, what's the first one? What are we looking at? H equals 12 and h equals 2. So let's plug in 12. That's going to equal 16 over pi times 12 squared times dv dt, which they gave us. What was it? What was it? It was negative 2. Negative 2. Now simplify that even more. So we got 12 squared here, and that's really 144. And 16 and 144 simplify. It goes in 9 times. So this is really 9 pi. So I'm going to have a negative 2 on top, and on bottom I'll have a 9 pi. Now let's talk about units. We have units in here. We're talking about h. It's a single dimension. And the measure of our dimensions were in terms of meters. So this is negative 2 over 9 pi meters per, is it second? Probably. Yes, meters per second. And then we got to do the second one here, because that was at h equals 12. But they want to know h equals 12 and h equals 2. dh dt at h equals 2, it's going to be equal to 16 over pi times the h squared, and in this case h is 2, times dv dt, which is negative 2. Okay, let's simplify. So we would get this 2 squared and the negative 2, those would simplify to negative 1 and a 2 on the bottom. So then I'll have negative 16 on top and 2 pi on bottom. That would simplify even more. The 2 and the 16 would become negative 8 on top over pi. What's our units? Same thing as last time. Meters per second. So notice kind of the process that we went through here. First we're looking at trying to find some type of primary equation that uses the given and the conclusion pieces. Because they got to both be there. We got to be able to plug in what we know and find what we don't. So, and then we need sometimes, especially in this case, possible a second equation or relationship for substituting. Then we take ddt of everything, substitute values, and then solve. That's a lot of steps. But these first two, these prep type steps, are huge. Taking the derivative with respect to time is big too, but those first two prep steps, if you don't have those straight, there's no way you'll even get close. Okay, so that's this part 3. I'm going to try and get the other parts done as well. let's see if we can get this uploaded. Thank you guys, and have a good night.